Hi, thanks for joining me today. I'm going to be going over a really fundamental theorem in the world of probability, and that is the weak law of large numbers, which essentially says that if you do things loads of times and take their average, it's going to tend towards the mean. Okay, so let's write that, or say what that is mathematically, and then I'll get into the proof. Okay, so we have x1, x2, all the way up to xn being IID random variables. So what does IID mean? Well, that just means they're identically distributed and they're independent from one another. So for example, each x1, x2, all the way up to xn could just represent a different coin flip. So obviously, if you're just flipping a coin, they're going to be identically distributed and clearly they're independent from one another. What I flip on the first row is not going to sort of affect what happens on the seventh row, for example. Anyway, these random variables have a finite mean mu, and variance sigma squared, where sigma squared is strictly between 0 and strictly less than infinity. Then for any epsilon bigger than 0, so any small positive number epsilon, this thing here holds. So the probability that the difference between x1 plus all the way up to xn divided by n minus mu, in other words, the distance between this thing here and the mean mu is less than epsilon, is going to tend to 1. So in other words, this guy here is going to tend towards the mean mu, which is exactly what I said at the start. The mean of all these random variables is going to tend towards the mean mu. Anyway, I'm going to be proving this theorem. Let's get stuck in. Okay, so the first thing we actually have to do is prove Markovs inequality. So this is this sort of statement here. We have a non-negative random variable t. So a random variable where t is bigger than or equal to 0, so non-negative. And a here is just some positive real number. Then I claim that the probability that t is at least a is less than or equal to the expected value of t divided by a. Okay, so let's get into the proof of this. So we're going to start with the expected value of t and use the law of conditional probability to just say that this thing here is the expected value of t given t is bigger than or equal to a times the probability that t is bigger than or equal to a plus the expected value that given that t is less than a times the probability that t is less than a, like so. Well, now let's just straight away jump in with an inequality. This thing here, expected value of t given that t is bigger than or equal to a, we don't really know what it is, but we know that this term here is going to be at least a, because we're computing the expected value of t, but we already know that it's at least a, so its expected value thus must also be at least a. So we get a greater than or equal to a from this thing here, and the probability that t is greater than or equal to a, I'm just going to keep the same. Now this thing here, I'm actually just going to throw in the bin. I'm going to disregard because the expected value of t given that t is less than a, well, we don't really know what it is, but we already know from assumption that t is at least 0, so its expected value will always be at least 0, even when we're given more information about it. So this term here is going to be at least 0, and this guy here is a probability, so it's also at least 0. Multiply them together, and you're also going to get some number which is at least 0. So this thing here, I'm just going to swap for 0, and this greater than or equal to sign takes care of that. So I've got the expected value of t is greater than or equal to a times the probability that t is bigger than or equal to a. Then just divide through by a on both sides, remembering that a is positive, so that won't affect the inequality, and you're going to get this thing here. So that's Markovs inequality proved. The next thing I need to do is prove Chebyshevs inequality, and then we'll be able to prove the weak law of large numbers. Okay, so here's a Chebyshevs inequality. We have a random variable z with finite mean and finite variance. Then, for any positive number epsilon, even if it's really small, we have that the probability that the distance between z and its expected value being bigger than or equal to epsilon is less than or equal to the variance of z divided by epsilon squared. Let's quickly prove this, and to prove this we're going to be using Markovs inequality, except our t now is just going to be z minus the expected value of z all squared. Okay, and clearly this is a non-negative random variable. I should have perhaps said that z is a real random variable, but hopefully that's kind of implied. But t is z minus the expected value of z all squared, like so. So this thing here is going to be non-negative, and our a is going to be epsilon squared. Okay, so this probability here, I'm just going to call it p for now. P we have is equal to this thing here, But notice that this inequality is also the same thing as if I just square both sides. So this is equivalent to z minus the expected value of z, this thing here squared being bigger than or equal to epsilon squared, like so. Okay, well, why is this true? Because this thing here is a non-negative quantity, so when I square both sides, I don't have to worry about some silly negative numbers in there. So this thing here is equivalent to this thing here, so their probabilities are going to be the same. And now I can just straight away apply Markovs inequality, noting that this thing here is just t. So the probability that t is bigger than or equal to epsilon squared. Well, then this thing here from Markovs inequality is less than or equal to the expected value of t divided by epsilon squared. But what is the expected value of t? Well, it's the expected value of this guy here, but that by definition is the variance of z. So this thing here is the variance of z divided by epsilon squared, like so, and we've proved Chebyshevs inequality. Now we can use this to prove the weak law of large numbers. Okay, so we've just shown Chebyshevs inequality, this guy here, and now just for simplicity, I'm going to let Sn be equal to x1 plus x2 plus all the way up to xn divided by n. Okay, and of course we want to show that xn kind of tends towards the mean mu. But firstly, let's work out the expected value of Sn and the variance of Sn. Well, the expected value of Sn is just going to be equal to, by linearity, we can just take out the 1 over n, and then it's going to be equal to the expected value of x1 plus dot 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 all the way up to the expected value of xn, like so. But each of these guys here are just mu, and there are n of them, so it's going to be n times mu, and then timesing by this 1 over n, we're going to get 1 over n times n mu, which is just mu. So all in all, the expected value of Sn is just mu. Great. What is the variance of Sn? Let's write it here. I'll write it here, sorry. Variance of Sn. This thing here, well, it's not linear, but if you're multiplying by this constant 1 over n, we have to square it to bring it out. So this is equal to 1 over n squared times the variance of x1 plus all the way up to xn. But each of these guys here are independent, and because of that, I can write this as the sum of the variances. So this thing here is equal to 1 over n squared times the variance of x1 plus dot 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 all the way up to the variance of xn. But each of these guys here, I can't remember if I called it something, but let's call it sigma squared. So this is equal to 1 over n squared times n sigma squared. So all in all, this is just sigma squared over n, like so. So the expected value of Sn is just mu, and the variance of Sn is just sigma squared over n. Now we're just going to directly apply Chebyshevs inequality. So plugging z equals Sn, you get the probability that Sn minus the expected value of Sn, which is just mu, being greater than or equal to epsilon, is less than or equal to the variance of z, which is just sigma squared over n, and then dividing that by epsilon squared, like so. And now very clearly here, remember we're fixing epsilon first to be some positive number, and then we're taking n to infinity. So this right hand side, we have epsilon already kind of fixed, and then if we take n to infinity, we see this right hand side here, because sigma squared is finite, this thing here is going to tend to 0. And of course, probabilities have to be at least 0. So by sandwiching this guy here between 0 and this thing here, which is going to 0, we get that this thing here must tend to 0. So this thing here tends to 0. Well, what does that tell you about the probability that Sn minus mu is less than epsilon? Because these two things here are sort of the complements of one another because of the change in inequality. So if this thing tends to 0, then this thing here must tend to 1, as n tends to infinity, and that's exactly what we claimed about the weak law of large numbers, except of course we had Sn written as this guy here. Okay, and that proves the weak law of large numbers. So all in all, it actually wasn't too difficult. We needed Markov, and then that gave us Chebyshev, and then this is just a special case of Chebyshevs inequality. Anyway, I hope you have enjoyed this video, a very, very fundamental result of probability. Thanks for watching. I'll catch you in the next one. Have a great day.